Section 10.2, we're going to continue our work with quadratic equations and graphing, but this time we're going to be solving equations. So let's take a look at what that means. So a quadratic function in standard form, f of x, or we can use the term y, equals ax squared plus bx plus c. There's some things we need to know about this. First of all, when we graph a function like we did in section 10.1, we're showing all the possible x, y solutions of the function. So we set up a table and we get maybe 5 different values, but as soon as we draw the curve through those points, we're showing every single possible x, y solution that would make this statement true. When we set a function equal to 0, we solve for the x values that make y equal to 0. So if I take this same function, and again using the general form, if I now solve for x, I am finding the 1, or in most cases with a quadratic, 2 x values that make y equal to 0. As we learned with our linear equations, when you set y equal to 0 and you solve for x, we are finding the x-intercepts. So this quadratic set equal to 0, when I find these 2 points, the values of x that make y 0, those are my x-intercepts. We also call these the roots or the zeros of the equation. So if we solve an equation by graphing, we graph the entire function and then look for the x-intercepts for our solutions. All right, let's try one together. So if I want to solve 0 equals x squared plus 2x minus 8 by graphing. So first I'm going to graph the entire function, y equals x squared plus 2x minus 8. So just like in the last section, negative b over 2a gives me my x value. In this case, negative 2 over 2 times 1, or negative 1. I set up my table of values with negative 1 in the middle. And I've already done this ahead of time. If you'd like a little more practice on setting up your table of values, go ahead and do this on your own and then pause the video and come back. So negative 3 is negative 5. Negative 2 is negative 8. Negative 1 is negative 9. 0 is negative 8. And 1 is negative 5. So I'm going to plot these, and let's see, I need more negatives than positives. So I'm going to set my x-axis a little bit higher than normal. So negative 3, 1, 2, 3, 4. Oops, that's only 4. Negative 5. Okay. Negative 3, 1, 2, 3, 4, 5. Yep. Negative 2 down to negative 8. Negative 1, negative 9. 0, negative 8. And 1, negative 5. Now, to solve this equation, I now want to know what x value makes y 0. In other words, where does this graph cross the x-axis? Well, I can't really tell exactly. I know it does something like this, but it's hard to tell exactly where it's going to cross. So I'm going to go ahead and see if I can find some more numbers on either side. I'm going to stick negative 4 up here. If I stick in negative 4, I have negative 4 squared plus 2 times negative 4 minus 8. That's 16 minus 8 minus 8. There we've got our y equals 0. And if I go to 2, 2 squared plus 2 times 2 minus 8 is 4 plus 4 minus 8. And there's my other 0. So 2, 0 and negative 4, 0 are the 2 places where this quadratic equation has a y value of 0. Okay, so I found my two solutions. The solutions to this equation are x equals -4 and x equals 2. Now I want to go back for a minute and remember how we solved this before. Remember our factoring. X minus 2, x plus 4, factors of -8 that add up to 2. X minus 2 equals 0. X plus 4 equals 0. So x equals 2 and x equals -4. Now, at this point, this seems like an easier way to solve this equation than setting up this table. However, you will find that there are times when we don't get nice, neat quadratics that we can factor. All right, let's look at a couple more things about zeros. You notice that there are two solutions to this parabola, two x values that make it equal 0. Quadratic equations always have two roots. Remember again, that means two x-intercepts. So we can have two distinct real roots, like we did on the last one. We can have a parabola that crosses the x-axis in two places, and we have two distinct real roots. It's also possible to have two identical real roots. In other words, the parabola only touches the x-axis in one place, but I'll show you why there are two identical roots for that one spot. The other possibility is two imaginary roots. Imaginary roots are roots or zeros that do not cross the x-axis. So if my parabola never crosses the x-axis, we can say it has no x-intercepts, but we still say it has two imaginary roots. We'll learn more about this as we go through, but I need you to know that there are always two roots, even if we can't see them on a graph. Okay, let's try this one. So to solve this equation, the first thing I have to do, just like when I was doing my factoring, is put everything on one side and set it equal to 0. Go ahead and find my axis of symmetry, -b over 2a. In this case, -4 over 2 times 1, or -2. Set up our table with -2 in the middle. So I need -3, -4, -1, and 0. If I put in -4 for x, that gives me +16 minus 16 plus 4. If I plug in -3, I get +9 minus 12, that's -3, plus 4 is 1. -2, +4, -8, +4, that's 0. If I plug in -1, I get 1, and if I plug in 0, I get 4. Go back. So let's plot this. -4, 4, -3, 1, -2, 0, -1, 1, and 0, 4. You can see I have only one x-intercept. However, if I solved this equation with factoring, my factors would be x plus 2, x plus 2. So notice that if I separate my factors to solve for 0, I do get two solutions. They just happen to be identical solutions, which means that the parabola only touches the x-axis in one place. There is only one x-intercept, but there are two solutions or roots. Okay? It's a little bit of a distinction, but we're going to talk about this together as well. All right, let's try another one. Here's another one, set equal to 0. set up my table using my negative b over 2a. So it's negative of negative 4 over 2 times 1, which is positive 2. There's my middle. Again, I'm going to go 0, 1, 2, 3, and 4. I've done this ahead of time, but I get 4, 1, 0, 1, 4. Plotting this, 2, 0, 1, 1, 0, 4, 3, 1, and 4, 4. Again, one x-intercept, but look again what happens if I factor this, minus 2, get x equals 2, x equals 2. Again, two solutions, two roots. Another way to say it is two zeros. Those all mean the same thing, but there's only one x-intercept on the graph because they are duplicate solutions. Okay, let's look at one more here. So again, setting this equal to 0, adding 6x. Finding my negative b over 2a. Negative 6 over 2 times 1 is negative 3. So negative 3 is the center, using negative 4, negative 5, negative 2, and negative 1. Negative 5 will give me 25 minus 30, which is minus 5 plus 2 is 2. Negative 4 will give me 16 minus 24 plus 7. That gives me negative 1. Negative 3 gives me negative 2. Negative 2 gives me negative 1, and negative 1 gives me 2. So let's see what happens here. 1, 2, 3, 4, 5, negative 5, 2. Negative 4, negative 1. Negative 3, negative 2. Negative 2, negative 1, and negative 1, 2. Now if I plot these, I do cross the x-axis, but not on a whole number. So my x-intercepts are between negative 1 and negative 2, and between negative 4 and negative 5. Let's go back and try to factor this and see if we can get some better solutions. What are the factors of 7 that add up to 6? Well, you might think it's 7 and negative 1, but that won't work because that would multiply to negative 7. There are no factors. This is a prime quadratic equation. It cannot be factored. So the only way to even get close to the possible x-intercepts are by graphing.